Welcome to the Explainer. Today, we're taking a deep dive into textbook calculus, but we are absolutely stripping away the terrifying math. Instead, we're going to show you how all those complex formulas perfectly match your everyday physical intuition of the world. Seriously, if you've ever stared at a page of derivatives and felt completely lost in a sea of symbols, you are exactly in the right place.
So let's dive right in with what sounds like a completely crazy question. How can the exact same intuition a toddler has on a playground slide help you conquer rigorous differential calculus? It sounds wild, I know, but the foundational logic of calculus is quite literally built on everyday, intuitive physical movement.
We're going to level up through 6 quick steps today. We'll start with the intuition of a slope, tackle the problem with curves, introduce the first and second derivatives, find our maxima and minima, and then, finally, put it all to work.
All right, step 1. The intuition of a slope.
Just think about a playground slide for a second. If you're climbing upward, the slope is positive. If you're sliding downward, it's negative. And if you're just sitting completely flat, well, the slope is 0. It's that simple. And honestly, that right there is the fundamental baseline for everything we're going to cover today.
So what does slope actually mean mathematically? Well, if you walk 10 meters forward on a perfectly straight road and the road rises 2 meters, your steepness is calculated by dividing that rise by the run. That's 2 divided by 10, which gives you a constant slope of 0.2 everywhere on that line. Every single time you move forward, the steepness stays exactly the same. No surprises.
Moving on to step 2, the problem with curves. This is where things start getting interesting.
Think about your classic curve, y equals x squared. You absolutely cannot just say this curve has a slope of 2 like we did with that straight road. Near the bottom, it's almost totally flat, but as you move farther to the right, it becomes incredibly steep. The slope is constantly changing depending on exactly where you happen to be looking. And you know what? That right there is the central problem of differential calculus.
So how on earth do we pin down a slope when it refuses to stay still? Well, we have to understand the difference between a secant and a tangent. A secant is really just a straight line joining 2 separate points on a curve. It gives you an average. But to find the slope at one exact specific point, you have to imagine zooming in extremely close to the curve until it practically looks like a straight line. That perfectly matching line that touches at exactly one microscopic point, that's your tangent. It gives you the exact instantaneous direction.
Which brings us nicely to step 3. Enter the first derivative. I know the word derivative can sound pretty intimidating at first, especially with all those limits and dy over dx fractions. But don't let the notation scare you off. It simply means finding the instantaneous slope of that tangent line we just talked about. You do this by taking a secant line between 2 points and moving those points closer and closer and closer together until the distance between them is essentially 0. That's all the limit is.
And this is where the absolute magic of calculus shortcuts comes in. Doing limit math every single time you want a slope? Exhausting. But calculus gives us a rule. Take the curve y equals x squared. Its derivative is just 2x. Instead of tedious, page-long calculations, this little rule tells us exactly how steep the curve gets. When x is 1, the slope is 2. When x is 2, the slope is 4. When x is 3, the slope is 6. You can literally just plug the numbers in and see exactly how the steepness increases.
All right, step 4, decoding the second derivative.
Let's use a super intuitive picture for this, riding a bike. The first derivative is simply whether you are pedaling uphill or downhill. Easy, right? But the second derivative, that tells you whether that hill is getting steeper or flatter. It answers the question, are you about to struggle way more, or is the climb finally easing up?
And hey, this maps beautifully onto physics too. If you track your position over time, the first derivative is your velocity, literally how fast you're moving. The second derivative is your acceleration, how your speed itself is changing. This is exactly why your textbook compares second derivatives to acceleration. It's the change of the change.
Step 5. Finding maxima and minima, the turning points.
Picture a ball rolling up a hill. At first, it has an upward positive slope. Eventually, it rolls down the other side with a negative slope. But at the very top, for just one fleeting microscopic instant, the slope is perfectly flat. That means the first derivative equals exactly 0, creating a maximum point. And the exact same logic applies to finding a minimum in a valley, just in reverse.
So, the crucial point your textbook always wants you to memorize is the second derivative test. Basically, if your first derivative is 0, you immediately check the second derivative. If it's less than 0, meaning the slope is decreasing or concave downward, boom, you found a maximum peak.
But if it's greater than 0, meaning concave upward, you've found a minimum valley. I know it feels a tiny bit backward at first, but physically it makes total sense.
Finally, step 6, putting calculus to work. Now that we've got all this conceptual scaffolding built, let's actually use it. Think about the classic textbook box problem. You're cutting squares from a 20 by 30 piece of cardboard to fold a box, and you want to find the absolute maximum volume. You end up with an equation, v equals 600x minus 100x squared plus 4x cubed. But the big question is, why do we bother differentiating this equation we just made?
The answer is actually elegantly simple. We differentiate it because finding the largest possible volume literally means finding the absolute highest point on the graph of that equation. And as we just learned, at the highest point, the turning point, the tangent is totally horizontal. Therefore, the first derivative simply must be 0.
It's pretty awesome when you notice how it all connects, right? This entire chapter of your textbook can be viewed as one unbroken logical chain. It seamlessly links a curved line to its slope, to the tangent, to the first derivative, all the way to rigorous maximum and minimum volume calculations using the second derivative test. You literally just walk down the steps.
Honestly, if you only remember one single thing from this explainer, make it this golden rule. The first derivative tells you how steep the curve is, and the second derivative tells you whether that steepness is increasing or decreasing. This one idea is the master key that unlocks almost everything in your calculus class.
So we've successfully taken the intimidation out of the notation. You've leveled up from a toddler slide all the way to mastering the second derivative test. The question now is, since you can visualize exactly what calculus is doing behind the scenes, how is this going to change the way you look at the physical world around you? Keep this intuition in your mind and see if you can spot the hidden derivatives in your everyday life. You've totally got this.